How do you measure the immeasurable? How do you grasp a reality that stretches beyond the reach of time, yet dances upon the trembling edge of the smallest particle? The universe begins not with an answer, but with a question that hums in every corner of existence, a question older than the first starlight and as intimate as your own breath. Look upward. Galaxies whirl in silent symphonies, immense spirals of matter colliding in a slow, eternal ballet. Their ancient light travels across billions of years, only to meet your gaze in this fleeting moment. Yet beneath the grand sweep of these cosmic cathedrals, something even stranger is at play. At scales too small for the naked eye, quantum particles flicker like ghosts, appearing, vanishing, reappearing as if reality itself were an elaborate sleight of hand. Here, certainty dissolves. A particle may be in two places at once, or perhaps in no place at all until we dare to look. The laws of physics, once thought to be written in the ink of absolute precision, reveal a hidden flexibility, a world where probability replaces predictability and observation itself shapes what is observed. Consider the tension. On one side, the measurable universe planets obey the firm tug of gravity, the orbits of stars mapped with mathematical clarity, equations that predict eclipses centuries before they occur. On the other, the unfathomable microcosm where the very act of measurement disturbs the thing being measured. These two realities, vast and microscopic, predictable and unknowable, are not separate stories. They are one continuous riddle, and within that riddle lies the pulse of a deeper mystery: consciousness itself. What is it that allows you, a thinking being made of atoms forged in ancient stars, to witness this spectacle at all? You are not merely a spectator. You are part of the very cosmos you strive to comprehend. Your neurons, sparking with electric whispers, echo the patterns of the galaxies above. The hydrogen that fuels the sun burns also in the hemoglobin of your blood. To know the universe is, in some strange and quiet way, to know yourself. Yet the bridge between the cold certainty of physics and the warm immediacy of awareness remains elusive. Science gives us the language of numbers, of particles and forces, of space-time and entropy. Philosophy gives us the language of meaning, of experience and mystery, of questions that cannot be captured in equations. Between them stretches a landscape both treacherous and sublime. We stand at its edge, drawn by curiosity, yet humbled by the immensity of what we cannot yet explain. Can the same universe that yields to mathematical scrutiny also cradle the unfathomable spark of self-awareness? Or are we forever to live in the tension between what can be measured and what can only be felt? Every discovery has deepened the paradox. The more precisely we chart the cosmos, the more we are confronted by its strangeness. Dark matter and dark energy realities that outweigh the known universe remain invisible, inferred only through their gravitational whisper. The quantum realm defies classical logic, challenging even the most disciplined minds to reconcile particle with wave, determinism with chance. And consciousness, our own direct experience, refuses to be reduced to mere neural circuitry. It lingers like an unanswered echo, a presence that resists every tidy definition. This is no ordinary puzzle. It is a cosmic riddle that invites wonder rather than resolution. To step into it is to accept that awe is not a weakness of understanding, but a necessary companion to discovery. Wonder sharpens our questions, and questions ignite our search. We are explorers not only of space and time, but of the mystery of being itself. So let us begin where all great journeys start, not with certainty, but with curiosity. The universe, vast beyond imagining and subtle beyond reason, calls us to listen. Somewhere between the measured and the mysterious, between the infinite expanse of galaxies and the flicker of the quantum, lies a truth we have yet to name. And perhaps in seeking it, we will come to see that the story of the cosmos is also the story of us. The classical foundation. From Newton to Einstein, imagine standing beneath a night sky so clear that every star seems carved in diamond against the infinite black. For centuries, humanity gazed upward and believed the heavens to be a realm of perfect order, a cosmic clock whose every gear and wheel ticked with divine precision. The planets followed their stately paths. The moon's cycles arrived like the turning of a flawless mechanism. To the human mind hungry for certainty, this celestial regularity whispered a single, intoxicating promise: the universe is knowable. It was into this world of wonder and ambition that Isaac Newton stepped, a quiet genius who transformed scattered observations into a single, monumental vision. In the 17th century, a time when science was still finding its voice, Newton's Principia forged the laws of motion and the universal law of gravitation. With a few simple equations, he bound apples to planets, explaining how the same force that tugged fruit toward the ground also guided the moon across the sky. For the first time, the heavens and the earth were no longer separate kingdoms, but one continuous realm ruled by the same immutable rules. Newton's universe was mechanical, but not cold. It carried the elegance of a grand design, a cosmic architecture of infinite reach. The world became a vast celestial clock, every cog and pendulum moving in precise harmony. Predictability reigned. Given the positions of all the planets and the forces between them, one could, in principle, calculate the entire future and retrodict the entire past. Determinism, this bold belief that the universe unfolded like a perfectly written script, became the heartbeat of classical physics. This vision offered comfort as much as it offered knowledge. Nature was not chaos but choreography. Even the wildest storms or the most distant stars obeyed laws that never wavered. Philosophers and mathematicians drew strength from this discovery. If reality was indeed a grand machine, then every mystery could be unraveled by reason. Laplace, the great French mathematician, took Newton's ideas to their logical extreme. He imagined an intellect later called Laplace's demon, who, knowing the position and momentum of every particle, could predict every future event and recall every past one. For centuries, this demon haunted science as an emblem of absolute certainty. Yet within the very triumph of this mechanistic worldview lay its first seeds of unease. A clockwork universe leaves little room for freedom or novelty. If every atom's dance is determined, where do choice, chance, or wonder truly dwell? For philosophers, this deterministic cosmos provoked both awe and quiet dread. But for scientists of the 18th and 19th centuries, it was a golden age of confidence. From the orbits of planets to the flight of cannonballs, from tides to eclipses, Newton's equations mapped reality with unerring accuracy. By the dawn of the 20th century, it seemed that only a few loose ends remained minor clouds on an otherwise clear horizon. One of those clouds was the mysterious speed of light. Experiments showed that light traveled at a fixed velocity, no matter how fast the observer or the source moved. This stubborn constancy defied the expectations of Newtonian mechanics, which assumed that velocities should simply add or subtract like those of moving trains. Another puzzle was the odd behavior of Mercury's orbit. which deviated ever so slightly from predictions. Astronomers searched for hidden planets or subtle forces, but the answers lay deeper, in the very fabric of space and time. Enter Albert Einstein, a young Peyton Clark whose imagination reached beyond the boundaries of conventional physics. Where Newton envisioned space and time as a stage absolute, unchanging, and eternal, Einstein dared to question the stage itself. In 1905, his special theory of relativity declared that measurements of space and time were not universal, but depended on the motion of the observer. Lengths contracted, clocks slowed, and simultaneity, once a simple, shared experience, became a relative concept. The implications were staggering. The speed of light was not just a number, it was the ultimate speed limit, a cosmic constant woven into the structure of reality. Time and space were no longer rigid backdrops, but interwoven threads of a single fabric, space-time. And in this fabric, energy and mass revealed a hidden kinship, captured in the most famous equation of all, E equals mc2. Matter could become energy, energy could become matter. The universe itself was more fluid than the most daring minds of the classical age had imagined. Einstein did not stop there. A decade later, in his general theory of relativity, he transformed gravity from an invisible tug into a grand geometric dance. According to this revolutionary vision, massive objects like stars and planets do not pull on each other across empty space. Instead, they bend the very geometry of space-time around them. Planets orbit not because of an unseen force, but because they follow the natural curves of a warped cosmic landscape. Gravity was no longer a force in the Newtonian sense, but a manifestation of geometry itself. To visualize this, imagine placing a heavy sphere on a rubber sheet. The sphere depresses the sheet, and a smaller ball rolls nearby, spirals inward, not because of an invisible string, but because the surface itself is curved. Replace rubber with the fabric of the cosmos, and the image becomes a hint of Einstein's insight. Space and time are not inert. They are elastic, dynamic, capable of stretching, bending, and rippling like the surface of a vast, invisible ocean. The confirmation of this bold theory came in 1919, when Arthur Eddington's expedition observed the bending of starlight during a solar eclipse. Light from distant stars curved as it passed near the sun, exactly as Einstein predicted. Overnight, a quiet Peyton Clark became a global icon, and the Newtonian world, a world of absolute space and immutable time, gave way to something far more supple and strange. Here was the first great tension in modern physics, the contrast between the steady tick of Newton's cosmic clock and the pliable space-time of Einstein's universe. The classical dream of a perfectly predictable reality had not been destroyed, but it had been reshaped. Gravity was no longer a simple force. Time was no longer universal. Space itself was no longer a passive void. The very stage on which reality unfolds had become an actor in the play. And with this realization came a deeper humility. The cosmos was not merely a machine to be dissected, but a living geometry of staggering complexity. Predictions remained possible, but the ground beneath our equations had shifted. Certainty gave way to a more profound kind of wonder, the recognition that reality itself might be woven from principles beyond the reach of our oldest intuitions. Quantum dawn, the birth of uncertainty. The turn of the 20th century, when the smoke of the industrial age still clung to the cities of Europe, Science carried itself with the quiet pride of a discipline that believed it had nearly completed the map of reality. Newton's laws had reigned for more than 2 centuries, their precision and elegance offering a universe that felt as dependable as a clock. Celestial mechanics and terrestrial motion were bound by the same equations, and everything from the orbit of planets to the swing of a pendulum could, in principle, be predicted. It was a cosmos of certainty, an intricate machine whose cogs and wheels turned in obedience to immutable laws. Yet in the flicker of a new century's dawn, faint cracks began to appear in that grand mechanism. The first tremor came from a German physicist named Max Planck, who in 1900 sought only to solve a stubborn problem of blackbody radiation. The issue seemed a technical nuisance. Classical physics predicted an ultraviolet catastrophe, an infinite energy output at high frequencies that clearly contradicted experiment. Planck, in a move that would quietly ignite a revolution, proposed that energy was not continuous but came in discrete packets, quanta. It was a mathematical trick, or so he thought, a temporary measure to fit the data. But nature was whispering a truth far stranger than Planck himself imagined. Energy, the very currency of the cosmos, was not a smooth river but a cascade of indivisible drops. If Planck's quanta were the first breach in the wall, Niels Bohr's atom would widen it. Atoms, those ancient philosophical dreams now revealed through the new tools of physics, were expected to obey classical rules. Yet electrons orbiting a nucleus should, by those rules, spiral inward and collapse. Bohr's 1913 model defied that fate by declaring that electrons could occupy only certain energy levels, leaping between them in sudden quantized jumps. Light itself was emitted or absorbed in these leaps, tiny bursts of color that betrayed the atom's hidden structure. Here was a vision of matter that flickered and danced rather than flowed, an architecture of abrupt transitions, a universe built from steps rather than slopes. But even as Bohr's model explained the spectral lines of hydrogen, it carried an unease. How could electrons, particles of definite mass and charge, leap from one orbit to another without traversing the space between? Classical intuition found no footing. The atom had become a stage for discontinuity, a theater where particles performed impossible acrobatics. Bohr himself sensed that something deeper lay beneath his equations, a principle that would rewrite the grammar of reality. That principle began to surface in the hands of Werner Heisenberg. Restless and brilliant, Heisenberg sought a theory that dispensed with the comforting image of electron paths altogether. In 1925, he forged matrix mechanics, a formalism that focused not on trajectories, but on observable quantities, frequencies, intensities, measurable facts. And from that abstraction emerged a revelation both precise and unsettling, the uncertainty principle. One could never know both the position and momentum of a particle with arbitrary accuracy. The more sharply one measured where a particle was, the more blurred became its motion. The more clearly one tracked its motion, the more its location dissolved into probability. This was not mere experimental clumsiness, not a limit of our instruments. It was a statement about nature itself. Reality, at its smallest scales, refused to be pinned down. The solid ground of determinism gave way to shifting sands of probability. Heisenberg's principle was not just a technical rule, it was a philosophical thunderclap, announcing that the dream of perfect knowledge of the Newtonian ideal had been irrevocably broken. As Heisenberg dismantled certainty, Erwin Schrödinger offered a picture equally haunting and beautiful. In 1926, he introduced his wave equation, describing particles not as discrete points but as undulating waves of probability. An electron in an atom was not a tiny billiard ball orbiting a nucleus, but a misty cloud of possibilities, a ripple of potential being. Measure it, and the wave would collapse, yielding a definite outcome, but only at the moment of observation. Until then, the electron's state was a superposition of all possible locations and motions. This idea defied the very notion of an objective world existing independent of us. Observation, once the passive act of recording reality, became an active participant. In the quantum realm, to look was to influence, to measure was to create. It was as if nature concealed a deck of cards until the instant we lifted the veil, revealing not what was, but what could be until it was forced to choose. For philosophers and physicists alike, the implications were dizzying. Centuries of belief in a universe governed by unbroken chains of cause and effect suddenly seemed parochial. The clockwork cosmos of Newton yielded to a shadowy theatre of chance. The scientist's dream of a complete and certain knowledge now faced an elemental boundary, an indeterminacy woven into the fabric of existence. Some, like Albert Einstein, recoiled. "God does not play dice," he famously declared, convinced that quantum mechanics was incomplete, that hidden variables must lurk beneath the apparent randomness. Others, including Bohr, embraced the paradox, arguing that nature itself was fundamentally probabilistic. The debate between Einstein and Bohr became a philosophical duel, a clash of worldviews, the old guard of determinism versus a new vision, where uncertainty was not ignorance, but essence. As these ideas spread, the very meaning of reality shivered. Was the universe a grand machine, its future locked into its present, or a living tapestry of possibilities where the observer's gaze wove one thread rather than another? Quantum mechanics offered no comforting final answer, only equations that worked with uncanny precision while leaving the metaphysical ground unsettled. The early decades of the 20th century thus witnessed not merely a scientific revolution, but an existential awakening. The birth of quantum theory revealed a cosmos at once intimate and elusive, a reality that dances on the edge of knowing. What had begun as a quest to understand light and matter had become something far greater, a confrontation with the mystery of existence itself, where certainty dissolved and the universe unveiled its most profound secret, that at its heart, reality is not a solid edifice, but a shimmering field of possibilities. The observer's paradox, consciousness in the equation, in the silent theatre of the quantum world. Even the smallest act of looking seems to change the play. Imagine a particle, a single electron set free, to dance toward a screen with two narrow slits. Logic whispers it should pass through one slit or the other, leaving a pair of tidy marks. But when no one watches, the electron does something astonishing. It behaves like a wave, rippling through both slits at once and painting a delicate interference pattern of light and shadow. The universe, it seems, holds a secret choreography hidden from casual eyes. Then the curtain rises on the observer. The moment we decide to measure which slit the electron travels through, the elegant wave collapses. The interference vanishes. The electron, as if caught in the act, chooses a single path, leaving a single mark. Observation itself rewrites the story. This is the celebrated double-slit experiment, and it challenges the most basic assumption of science that the world exists independently of us. From these eerie results arose the Copenhagen interpretation, led by physicists like Niels Bohr and Werner Heisenberg. They proposed that quantum particles do not possess definite properties until they are observed. Reality, in this view, is not a solid stage set waiting to be surveyed. It is a shimmering field of probabilities that crystallizes only when measured. The act of observation is no mere data gathering. It is a creative event. But what exactly counts as an observer? Is it the clicking of a Geiger counter, the flash of a camera, or the awareness of a conscious mind? Bohr spoke cautiously, insisting that measurement referred to an interaction with a macroscopic apparatus. Yet even this careful phrasing cannot escape the riddle. If measuring devices themselves are made of quantum particles, when does the blur of uncertainty finally give way to a definite fact? Somewhere, somehow, an indefinite world hardens into reality. Some physicists argue that consciousness must be the final link in the chain. The mind, they suggest, is not merely peering into the quantum fog, but actually forcing it to condense. This daring idea, sometimes called the consciousness causes collapse hypothesis, casts awareness as a hidden architect of the cosmos. To look is to bring forth, to know is to create. It is a vision both exhilarating and unsettling, as though each thought carries the weight of a cosmic decree. Materialists recoil at this notion. They argue that quantum measurement is simply a physical interaction. A particle strikes a detector, energy is exchanged, and the wave function resolves into an outcome. Consciousness, in their view, is a latecomer, a byproduct of neuronal processes, not a cosmic trigger. They warn that smuggling mind into physics risks replacing rigorous science with mystical speculation. For them, the observer's paradox is not about human awareness, but about how quantum systems become entangled with their surroundings until decoherence leaves only classical certainty. Between these poles stretches a philosophical battlefield. On one side, the defenders of pure physicalism, confident that nature's laws need no witness. On the other, those who suspect that mind is not an accident of matter but a fundamental ingredient of reality itself. Each camp offers compelling arguments and neither can claim a final victory. The debate deepens when we consider the famous thought experiment of Schrödinger's cat. Sealed in a box, the cat is linked to a quantum event, a decaying atom that may or may not trigger a vial of poison. Until someone opens the box, quantum theory says the cat exists in a superposition of life and death. Is the cat both alive and dead? Or does reality choose only when an observer peeks inside? The cat itself is conscious. Does it collapse its own fate? The question lingers like an unsolved riddle. Modern interpretations, from the many worlds view to quantum Bayesianism, attempt to sidestep the need for consciousness. The many worlds interpretation, for instance, declares that all outcomes occur, each in its own branching universe. There is no collapse, only an endless cosmic fractal of possibilities. Yet even this vision raises existential wonder. If every observation spawns a new reality, what does it mean to be the observer? Some philosophers of mind suggest a subtler path. Perhaps consciousness and the quantum world are two aspects of a deeper, unknown reality, neither fully reducible to the other. This neutral monism whispers that mind and matter are twin faces of a single coin we have yet to name. Others explore the idea of panpsychism, the proposal that some form of proto-consciousness pervades the fabric of existence, that the capacity for awareness is woven into the very architecture of space-time. Such ideas ignite both fascination and skepticism. To many scientists, they verge on metaphysics untethered from experiment. To seekers of cosmic meaning, they hint that our inner life and the universe's deepest laws are mysteriously entwined. Here, physics blurs into philosophy. The equations of quantum mechanics brush against the ancient question of what it means to know. The observer's paradox remains an open wound in our understanding of reality. Does the universe wait for us to look, or does it unfold indifferent to our gaze? Each experiment sharpens the mystery rather than dissolving it. As we probe deeper into the quantum realm, we find ourselves not merely mapping the cosmos, but confronting the enigma of our own awareness, an awareness that may be both question and key. Multiverse and many worlds, escaping the collapse. What if every decision you've ever made, every hesitation, every whispered what if has already splintered into a new universe? Imagine a reality where each choice is not merely contemplated but lived out elsewhere, where another version of you stands at every fork in the cosmic road, walking paths you will never see. This is no mere fantasy spun from late-night wanderings. It is the audacious promise of the many worlds interpretation, a theory born from the heart of quantum physics and daring enough to challenge our deepest intuitions about existence. The story begins in the 1950s, when physicist Hugh Everett grew restless with the prevailing view of quantum mechanics, the so-called collapse of the wave function. The idea that observation snaps possibilities into a single outcome felt to him like a magician's trick, a convenient but unsettling loophole. Why, Everett asked, should reality bend to the gaze of consciousness? His answer was startling in its simplicity: it doesn't. Instead of one fragile thread of actuality, the universe unfolds in a vast branching of possibilities, each as real as the one we inhabit. No collapse, no privileged observer, only a ceaseless splitting of worlds. To picture this, envision a grand cosmic tree whose branches grow faster than thought itself. Every quantum event, every flicker of an electron's path, every spin of a subatomic particle creates a fork. One branch where the electron spins up, another where it spins down, and countless more where every microscopic uncertainty unfurls into macroscopic consequence. These are not shadows or hypotheticals. In Everett's daring vision, each branch is a full-blooded universe, blooming in parallel to our own. This notion sweeps away the almost mystical role once assigned to human consciousness. The act of measurement no longer carries the power to sculpt reality. It merely reveals which branch we already occupy. For those uneasy with the eerie suggestion that mind conjures matter, the many worlds interpretation offers a kind of intellectual escape hatch. Reality, it says, is objective and relentlessly plural, independent of the observer's awareness. Yet this escape comes at a cost, a vertiginous multiplication of realities so vast it stretches the imagination to its breaking point. Modern cosmology adds fuel to this dizzying prospect. The multiverse hypothesis, emerging from the mathematics of inflationary theory and the strange implications of string theory, extends Everett's idea beyond quantum events. Here the cosmos itself may be but one bubble in an infinite froth of universes, each with its own laws of physics, its own galaxies, its own stories, unfolding in silence. Our universe, once thought to be everything, becomes a single note in an eternal symphony, a solitary ripple on an unbounded sea. Science lends these visions surprising credibility. The equations of inflation suggest eternal spawning of pocket universes. String theory's extra dimensions hint at countless possible cosmic architectures. Even the mysterious dark energy driving our universe's accelerated expansion whispers of domains beyond our cosmic horizon. None of these ideas prove the multiverse exists, but they give it mathematical room to breathe, transforming it from pure speculation into a serious frontier of physics. Yet awe quickly shades into unease. For every branch of Everett's quantum tree, for every bubble universe swelling beyond our reach, there exists another you, making choices you will never remember, living lives you will never touch. In one world you turned left instead of right. In another you never drew your first breath. If all these versions are equally real, what becomes of identity? What becomes of meaning when existence itself is infinite? Philosophers wrestle with the implications. Does the multiverse truly solve the riddle of observation, or does it simply multiply the mystery? We escape the notion that consciousness collapses reality, only to confront an endless hall of mirrors. Probability, once a measure of uncertainty, becomes a measure of self-location. Out of all the versions of you, in which do you find yourself? The question gnaws at the boundaries of science and metaphysics alike, challenging the very language of explanation. Skeptics caution that such theories risk sliding from physics into poetry. A hypothesis beyond empirical test, they argue, is no more than an elegant guess, without a way to peer across the cosmic foam or detect the hidden branches of quantum splitting. The multiverse may remain forever out of reach, an idea that dazzles the intellect while eluding the rigor of proof. Still, the allure persists. For some, the multiverse offers a grand unification of mystery and mathematics, a cosmos where the improbable is inevitable, where every possible history finds a home. For others, it is a reminder of our smallness, a humbling confrontation with the infinite. Whether salvation from the collapse of the wave function or simply a deeper abyss of wonder, the vision of many worlds leaves us suspended between exhilaration and vertigo, poised on the edge of a reality more immense than we can ever fully know. Entanglement and non-locality, nature's hidden web beneath the familiar surface of reality. There is a secret lattice of connections so strange that even Einstein, the master of cosmic order, shuddered and called it spooky action at a distance. This is the realm of quantum entanglement, where particles, light years apart, whisper to each other in perfect unison, defying every expectation of separateness. To step into this hidden web is to feel the ground of classical certainty tremble. Here, the universe behaves less like a collection of isolated fragments and more like a single, breathing whole. Imagine two particles born from the same quantum event, spinning away into the dark like twin sparks carried by an unseen wind. According to classical logic, once they part ways, their fates should unfold independently. No signal, no force, no physical bridge should tie their futures together. Yet the quantum world refuses to bow to that tidy picture. Measure the spin of one particle, and the other instantly reveals a correlated result, as if both have been quietly rehearsing a cosmic duet since the moment of their creation. It is not merely coincidence. It is an unbreakable pattern written in the language of probabilities, but performed with flawless synchronicity. Einstein, Podolsky and Rosen crystallized the tension in their famous 1935 paper, the EPR paradox. They sought to expose what they believed was an incompleteness in quantum theory, proposing that hidden variables and unknown details of reality must be at work behind the scenes. To them, the alternative was unthinkable, that the universe allowed instantaneous influence, as though a choice here could echo everywhere. At once, Einstein insisted that God does not play dice. Yet he also recoiled from the idea that nature would violate locality, the principle that nothing can affect something else faster than light. For decades, the debate simmered, a philosophical riddle disguised as physics. Then, in the 1960s, John Bell offered a daring way to test the untestable. Bell's theorem did not merely frame the question, it carved a sharp dividing line. If local hidden variables governed the quantum world, then certain mathematical inequalities, Bell's inequalities, would never be broken. If experiments defied those inequalities, the dream of a purely local reality would collapse. The world answered Bell with an unsettling whisper. In the 1970s and 1980s, Alain Aspect and others refined experiments that forced nature to reveal its cards. Time and again, entangled photons flouted Bell's inequalities. No hidden mechanism lurking in the shadows could explain the results. Local realism. Einstein's last bastion of classical order cracked under the weight of evidence. These experiments did not show faster-than-light signals in the ordinary sense. Nothing traveled from one detector to another. No message could be sent that way. Yet the correlations leapt across space with a precision that mocked the notion of independent parts. The universe, it seemed, carried an invisible thread that stitched distant events into a single fabric. Today, this once abstract mystery is no longer confined to philosophical debate. Quantum teleportation, a process that uses entanglement to transfer the state of a particle from one location to another, has been achieved in laboratories and across satellites orbiting Earth. No material particle leaps the gap. What travels is pure information, carried on the silent bond between entangled partners. To watch a quantum state dissolve in one place and reappear in another is to glimpse the universe performing a feat that borders on the mythic. Consider the scale of the challenge to our intuition. For centuries, we have pictured reality as a grand machine assembled from separable pieces. Cause follows effect along clear chains. Space is the stage where objects move and forces act. Entanglement shreds that picture. It hints that the most basic building blocks of nature are not isolated at all, but aspects of a single, undivided whole. This is not mere poetic flourish. The mathematics of quantum theory describes a universal wave function, a single pattern from which every local observation emerges. When we measure, we carve out a fragment of this larger reality, but the fragment retains a memory of the whole. The web of entanglement does not simply connect particles. It suggests that the entire cosmos may be woven from relational threads. And so we face a profound contrast. On one side stands the classical faith in locality and independent existence, our daily intuition that objects are self-contained, that events are separated by distance and time. On the other side rises the quantum evidence of instantaneous correlation, the stubborn fact that nature behaves as if distance is an illusion and separateness a convenient fiction. Philosophers and physicists continue to wrestle with this tension. Some embrace interpretations in which the wave function itself is real, a single entity spanning all space and time. Others imagine hidden dimensions or many worlds where entanglement is but a shadow of deeper geometry. Still others suggest that consciousness itself may be entangled with the universe's fabric, a speculation that drifts toward the mystical, yet finds strange resonance in the experimental facts. What remains undeniable is the feeling of wonder that entanglement inspires. It invites us to see the cosmos not as a mosaic of disconnected parts, but as a living, holistic network where every piece, no matter how distant, is quietly bound to the rest. In that hidden web, the old boundaries of space and time blur, and reality reveals itself as something far more mysterious and far more unified than our classical minds were ever trained to imagine. The cosmic mind, hypothesis, consciousness as fundamental. Across the long arc of scientific discovery, we have grown accustomed to thinking of the universe as a grand machine, a clockwork of particles and forces spinning in perfect indifference. We imagine matter as primary, consciousness as a late-arriving spark, an evolutionary trick of chemistry and neurons. But what if this familiar narrative is reversed? What if consciousness is not an accidental whisper in a cold void, but the very fabric from which reality itself is woven? This is the audacious suggestion of the cosmic mind hypothesis, an idea that rattles the foundations of both science and philosophy. It begins with a question as ancient as it is unsettling. What is the nature of consciousness? For centuries, philosophers and scientists have tried to reduce the mystery of experience to the firing of synapses, the dance of electrical signals in the brain. Yet, after decades of neuroscience and cognitive science, the so-called hard problem of consciousness, as David Chalmers famously named it, remains unsolved. How does matter, blind and unfeeling, give rise to the red of a sunset, the ache of longing, the taste of memory? Some thinkers argue that the failure may not be ours alone, that the very question might be misframed. Perhaps consciousness is not something to be produced by matter, but something that precedes it, something from which matter itself emerges. This is the intuition behind panpsychism, the ancient yet freshly revived view that mind is a basic feature of reality. Long before modern science, the philosopher Baruch Spinoza envisioned a single, infinite substance, both material and mental, an indivisible God or nature, of which every thought and particle is a mode. Centuries later, his vision finds echoes in the writings of contemporary philosophers like Galen Strawson and Philip Goff, who argue that the chasm between mind and matter may be illusory. For them, consciousness is not a rare miracle but a universal property, as elemental as mass or charge. To the scientific ear, such claims can sound like heresy. Physics has built its reputation on reducing phenomena to measurable causes, on the assumption that reality exists independently of our perception. The equations of quantum mechanics, no matter how strange, are treated as mathematical tools, not metaphysical pronouncements. To many physicists, the idea that electrons or quarks might possess some glimmer of awareness is as untestable as it is unnecessary. Why multiply mysteries? The skeptic asks. Is it not enough to describe the world without smuggling mind into every atom? And yet, the cosmos itself seems to whisper counter-arguments. Consider the riddle of quantum observation, the double-slit experiment, where particles behave as waves until measured, collapsing into definite states only when an observer looks. Some interpret this not as proof of cosmic mind, but as a reminder of the strange entanglement between observer and observed. Still, the very fact that reality resists a clean separation between the knower and the known invites deeper speculation. Could consciousness be woven into the quantum fabric, not as an afterthought, but as a prerequisite? Modern panpsychism does not imagine rocks or rivers holding human-like thoughts. Rather, it suggests that the raw, subjective spark experience itself is the primordial currency of existence. Individual minds, including our own, are not isolated anomalies, but localized expressions of a universal field of awareness. Just as countless waves rise and fall upon the same ocean, so too might every flicker of sentience be a ripple in a boundless cosmic mind. This perspective finds surprising resonance beyond philosophy. In the 20th century, physicist Erwin Schrödinger, a pioneer of quantum theory, drew upon Eastern philosophy to claim that the total number of minds in the universe is one. Likewise, the British mathematician and philosopher Alfred North Whitehead proposed that reality consists of occasions of experience, that every event, from the birth of a star to the blink of an eye, carries an inner aspect of awareness. These ideas blur the line between physics and metaphysics, suggesting that the universe is not merely a stage for consciousness, but a living process of experience. Such notions awaken both wonder and doubt. On one hand, the vision of a self-aware cosmos stirs something ancient in us, a sense that our longing for meaning is not misplaced, that our own awareness is a window onto the universe's own self-recognition. On the other, the sober voice of science demands evidence. How can one test a hypothesis that consciousness pervades everything? No telescope or particle accelerator can directly measure subjectivity. To many physicists, the cosmic mind remains a poetic metaphor, not a falsifiable claim. And yet, we must reckon with the stubborn fact that consciousness is the one thing we cannot doubt. We might question the existence of the external world, of matter, even of time itself, but the reality of our own experience is inescapable. In this light, materialism begins to look less like an obvious truth and more like an unexamined assumption. Perhaps it is not mind that must be explained away, but matter that must be reinterpreted. The tension between these worldviews, between the clarity of empirical science and the unsettling lure of a conscious cosmos, forms the heartbeat of this debate. It is a tension that has animated mystics and physicists alike, from the Upanishads to the cutting edges of quantum theory. Some will dismiss it as romantic speculation. Others will sense in it the first glimmer of a deeper understanding, one that unites the laws of nature with the mystery of awareness itself. Whether the universe truly knows itself, or whether our yearning for the cosmic mind is a reflection of our own, the question remains like a silent invitation. Perhaps in confronting this possibility, we are not merely studying the cosmos, we are participating in its own unfolding awareness, as if the universe were looking back through our eyes, seeking to understand what it has always been. The debate of materialism versus idealism in the grand theatre of human thought. Few rivalries shimmer with more tension than the contest between materialism and idealism. Imagine two ancient titans, one forged of atoms and equations, the other woven from pure awareness, locked in a dance that has shaped every philosophical age. Their duel is not a quiet one. It reverberates across laboratories and meditation halls. Through the writings of scientists and mystics, each side convinced it holds the master key to reality itself. Materialism steps forward first, cloaked in the authority of the modern scientific method. It is the worldview that claims the universe is a vast machinery of matter and energy, a clockwork cosmos where consciousness is not a cause but an effect. From this perspective, the mind is a latecomer, a byproduct of the brain's complex circuitry. Every sensation, every dream, every flicker of self-awareness is, in the materialist view, a pattern of neural firings no more mysterious than the spark of electricity through copper wires. The confidence of this stance is intoxicating. After all, the triumphs of science, from decoding the genetic code to detecting ripples in space-time, suggest that every mystery eventually bends to the tools of measurement. And yet, idealism raises an eyebrow. Long before the microscope or the particle accelerator, philosophers like Plato and later Berkeley proposed that mind, not matter, is the true foundation of existence. For them, the physical world is not an independent stage, but a grand projection of consciousness itself. In Berkeley's words, to be is to be perceived. The materialist might scoff, but idealism lingers like an unshakable riddle. If every scrap of evidence for matter is ultimately a perception, how can we prove that anything exists beyond experience? The Enlightenment tilted the scales toward materialism, driven by Newton's laws and the promise of a universe governed by precise mathematics. But the pendulum never stayed still. Immanuel Kant complicated the picture, arguing that while phenomena appear to us in space and time, the ultimate reality, the thing in itself, remains forever beyond the reach of pure observation. His critique left both camps uneasy. Materialists were reminded that science cannot claim to capture reality in its totality, while idealists found no easy path to proving that mind alone is sovereign. Fast forward to the age of neuroscience and quantum physics, and the duel intensifies. Neuroscientists map the architecture of the brain with dazzling precision. They can stimulate a region and trigger a memory, or watch consciousness flicker as a patient slips under anesthesia. These feats reinforce the materialist conviction that mind emerges from matter. But in the quantum realm, matter itself grows slippery. Particles behave as probabilities until observed, suggesting at least to some interpreters that consciousness plays a role in shaping reality. This is not a claim accepted by all physicists, yet it provides tantalizing fuel for the idealist argument that awareness is not merely an afterthought but an active participant in the unfolding cosmos. The debate deepens when considering the hard problem of consciousness, a phrase coined by philosopher David Chalmers. The materialist can chart every neural pathway, yet still cannot explain why subjective experience, what philosophers call qualia, should arise from mere electrical activity. Why does the firing of neurons give rise to the color red as we perceive it, or the ache of nostalgia? For idealists, this is precisely the point. Consciousness cannot be reduced to matter because it is the very canvas on which matter appears. Materialists counter with patience and progress. They argue that what now seems intractable may one day yield to deeper understanding, just as the once mysterious phenomenon of life itself was eventually explained by biochemistry. They point to incremental breakthroughs, brain-computer interfaces that read thoughts, imaging techniques that predict decisions before we are aware of making them. To them, consciousness is a sophisticated computation emergent from complexity. Mystery is not proof of metaphysical primacy. It is simply the frontier of science. Idealists, however, see an unbridgeable chasm. They invoke not only philosophy but also the testimony of mystics, the paradoxes of quantum measurement, and the irreducible nature of subjective experience. If every scientific observation is itself a mental event, they ask, how can the mind be secondary? Even the equations of physics are thoughts in consciousness. To the idealist, the universe is more like a dream than a machine, and matter is but a pattern in the infinite expanse of awareness. Between these poles, some thinkers seek reconciliation. Panpsychism, for instance, proposes that consciousness is a fundamental property of the universe, as intrinsic as mass or charge. This idea softens the materialist stance without fully surrendering to idealism, suggesting that mind-like qualities pervade all matter. Others, like the proponents of neutral monism, argue that reality is made of a single substance that is neither purely mental nor purely physical. These middle paths reveal how porous the boundary between science and metaphysics can be, and how each camp, when pressed, gestures toward the other. Yet the duel continues because it is not merely academic. The stakes are profoundly personal. If materialism is true, then consciousness is a brief spark in an indifferent cosmos, and meaning must be forged against the silence of the void. If idealism holds, then consciousness is the ground of all being, and death is less an ending than a transformation within a boundless mind. Each worldview carries existential weight, shaping our understanding of purpose, morality, and the nature of self. We live in an age where these questions are no longer confined to the philosopher's study. Advances in artificial intelligence challenge our assumptions about mind and machine. Experiments in quantum computing flirt with the interface between information and reality. Meanwhile, the human thirst for transcendence endures, from the meditation cushion to the particle collider. Materialism offers the comfort of clarity and the discipline of evidence. Idealism offers the allure of mystery and the possibility that consciousness is more than a flicker in the dark. As the debate unfolds, it becomes clear that neither side can claim final victory. Materialism provides the engines of technology and the power to predict, but it struggles to account for the raw fact of subjective experience. Idealism captivates with its poetic vision, yet wrestles with the stubborn reality of a world that resists mere imagination. Perhaps their conflict is less a battle to be won than a tension to be lived, a dialogue that keeps our sense of wonder alive. Time's illusion. Past, present, and the quantum flow time, we are told, is the silent stage upon which existence unfolds. It feels like the most obvious thing in the world, seconds ticking forward, the past fading into memory, the future still unborn. Yet the deeper we peer into nature's fabric, the more this comforting rhythm begins to waver, revealing cracks in the very idea of a flow. What if the rushing river of moments is only a trick of perception? What if the past and the future stand side by side with the present, already written into the cosmic script? Albert Einstein startled the world with this heresy. His theory of relativity does not merely tweak our sense of clocks and calendars, it dissolves the very notion of a universal now. In Einstein's equations, time is inseparable from space, woven into a four-dimensional continuum where all events, births, and deaths, galaxies forming and stars collapsing exist simultaneously, like scenes already etched on an eternal film reel. From this vantage, the present is no privileged slice of reality. It is simply the point our consciousness happens to occupy as it scans the real. Yesterday and tomorrow are equally real, their existence unshaken by our fleeting awareness. This block universe vision is both elegant and unnerving. If all moments exist at once, the flow of time we feel so intimately becomes a kind of cognitive mirage. Our sense of moving from cradle to grave might be no more objective than the sensation of motion we feel on a stationary train as another glides past. We are left with a disquieting question. If the universe is already complete, every decision, every heartbeat, every yet-to-be-spoken word already fixed, where does that leave free will? Are we actors improvising on a live stage, or characters reading lines that have been scripted since the dawn of creation? Philosophers wrestle with this paradox. Some argue that free will is compatible with a predetermined block, that choice is simply the internal experience of following a path that was always there. Others counter that such freedom is an illusion, a story we tell ourselves to give weight to our actions. Either way, the tension remains. Our lives feel like journeys, yet physics whispers that the journey is already complete. Quantum mechanics deepens the mystery. While relativity paints time as static, quantum theory hints at a universe where cause and effect can sometimes run backward. Experiments in retrocausality, from the famous delayed choice quantum eraser to intricate entanglement studies, suggest that actions performed in the present can influence outcomes seemingly set in the past. Photons behave as if they know what measurement will occur before that measurement is made. Such findings do not prove time travel or magic, but they unsettle the classical chain of cause, leading neatly to effect. If the quantum world allows for information to ripple backward, the arrow of time begins to look less like a one-way street and more like a landscape where past and future are delicately intertwined. In that landscape, the present is not a moving knife edge, but a perspective within a grand tapestry. We might picture time not as a flowing river, but as a vast, shimmering crystal, every facet representing a moment past, present, future, illuminated at once. Our consciousness, like a beam of light, traces a path through those facets, creating the illusion of succession. This conception does not merely stretch physics, it presses against the heart of human meaning. If the past and future are as real as the present, then your birth, your triumphs and losses, your final breath, are all eternally inscribed. Death loses some of its sting if the moments of our lives never truly vanish. Yet this same permanence can feel claustrophobic. Every choice predetermined, every possibility already resolved, and yet perhaps the mystery of time is not a prison, but an invitation. If free will is a story, it is a story that shapes the texture of experience. If the universe is a block, our consciousness may be the way that block becomes alive, the way eternity tastes the flavor of sequence. Science gives us equations. Speculation dares to ask whether awareness itself might be the true river, flowing not through time, but through an infinite present in which all times rest. In confronting time's illusion, we stand at the threshold between physics and philosophy, between evidence and wonder. The ticking of the clock has not changed, but our understanding of what it measures may never be the same. For in the quantum flow, past and future are not distant shores, but reflections of a reality far stranger and far more profound than the simple march of seconds we thought we knew. Bridging science and mysticism, where physics meets the sacred, the history of human thought is a long, restless search for the nature of reality. Scientists and mystics, though walking paths that seem to diverge, have always been driven by the same impulse, to pierce the veil of appearances and touch the hidden source of existence. One speaks in equations and experiments, the other in silence and metaphor. Yet as the discoveries of modern physics deepen, the distance between these two languages begins to collapse, and what once seemed irreconcilable now feels like a dialogue written across the stars. In the ancient Chinese philosophy of Taoism, the ultimate ground of being is called the Tao, an unnameable void from which all forms arise and into which all forms return. It is not a void of nothingness, but a fertile emptiness, a dynamic stillness brimming with potential. Thousands of years later, quantum field theory describes the universe as a seething vacuum, an ocean of fluctuating energy from which particles briefly surge into existence and dissolve back into the field. Physicists measure the zero-point energy of this vacuum and speak of virtual particles that appear and vanish in a quantum froth. Taoist sages and quantum scientists, separated by millennia and method, seem to be whispering about the same enigmatic ground, a presence so subtle that it looks like absence, and yet from it, everything is born. Consider the holographic principle, a bold conjecture in contemporary physics. It suggests that the three-dimensional universe we inhabit may be a projection of information encoded on a distant boundary, like a cosmic hologram. The idea, born from black hole thermodynamics and string theory, proposes that space itself is a kind of illusion, a display of deeper, hidden dimensions. Long before lasers and holograms, the sages of the Upanishads spoke of Maya, the grand illusion in which the world of forms conceals the eternal Brahman. The mystics taught that our senses deceive us, that the phenomenal world is a shimmering veil. In the physicist's holographic universe and the mystic's Maya, we find a common astonishment. Reality is not what it seems. But the parallels are not mere poetic coincidences. They challenge us to re-examine what we mean by knowledge. Science demands evidence, repeatable experiments, and mathematical rigor. Mysticism requires inner transformation, a direct encounter with consciousness beyond words. One path looks outward through telescopes and particle accelerators. The other turns inward through meditation and ecstatic vision. They could hardly be more different, yet both seek to dissolve the boundaries of the self and reveal a reality that transcends ordinary perception. The quantum world itself invites this tension. Quantum entanglement, Einstein's spooky action at a distance, shows that particles separated by light years can behave as if they share an invisible thread, responding to each other instantaneously. For mystics, who have long spoken of an underlying unity binding all things, this is no surprise. The Buddhist concept of Indra's net pictures the universe as an infinite web of jewels, each reflecting all others. Entanglement gives a scientific echo to this vision. The cosmos is not a collection of isolated parts, but a seamless whole in which distance is less real than relation. And yet we must be careful. The resemblance between mystical visions and quantum insights does not mean physics proves the mystics right. The language of science and the language of the spirit are not interchangeable. Equations are not mantras, experiments are not revelations. But the convergence of their imagery suggests that reality is stranger than either discipline alone can capture. The mystic's metaphors and the physicist's models are like two beams of light striking the same crystal from different angles, each revealing a different spectrum of the hidden whole. This interplay between evidence and mystery opens a fertile middle ground, a place where rational thought and spiritual intuition can converse without collapsing into each other. Take the notion of cosmic consciousness, a theme explored by philosophers from Plotinus to contemporary thinkers in consciousness studies. While physics has yet to measure consciousness in any laboratory, the very success of quantum mechanics forces scientists to confront the role of the observer. In quantum experiments, the act of measurement is not a passive recording, but an active participant in the outcome. The wave function, a mathematical description of probabilities, collapses when observed, giving birth to definite reality. Does this imply that consciousness creates the world? Most physicists would resist that leap, but the undeniable entanglement of observation and reality reopens questions once confined to the mystics. Is the universe at its root inseparable from mind? History shows how both science and spirituality have evolved through tension and revision. Early natural philosophers from Pythagoras to Kepler saw no boundary between the mathematical and the sacred. The scientific revolution later drew sharp lines, seeking certainty through empirical method and banishing metaphysics to the realm of faith. Now, at the edges of quantum gravity and cosmology, those lines blur again. Black holes challenge the very fabric of space-time. The Big Bang hints at origins beyond time itself. These are not merely technical puzzles, they are invitations to wonder, to ask the same timeless question the mystics posed: what is the source of all this? Even language strains to hold the mystery. When physicists describe quantum superposition or the curvature of space-time, they reach for metaphors as surely as poets. Mystics too confess that ultimate reality is ineffable, beyond the reach of words. The Tao that can be named is not the eternal Tao. The equations that can be written are not the final truth. Both science and mysticism are compelled to gesture beyond themselves, to acknowledge that the universe exceeds the grasp of any single description. Perhaps the most profound lesson of this convergence is humility. Science, for all its triumphs, reveals a cosmos that is vaster, older, and more intricate than we ever imagined. Mysticism, for all its inward clarity, reminds us that the deepest truths cannot be possessed, only experienced. When these two traditions meet, they do not cancel each other but amplify the sense of wonder. They invite us to live not in certainty but in curiosity, to embrace both the precision of physics and the silence of the sacred. To bridge science and mysticism is not to blur them into one indistinct path. It is to recognize that reality has more dimensions than any single approach can map. The physicist's equations and the mystic's visions are like two eyes of the same humanity. Only together do they give depth to the great mystery. And in that depth, we glimpse something both infinitely knowable and forever beyond our grasp. A cosmos that is at once a vast machine of law and a sacred field of meaning, inviting us to wonder without end. The human quest for meaning in a quantum cosmos, across the vast cathedral of the cosmos, the human heart beats with a single, unrelenting question: why are we here? We stand at the intersection of staggering scientific discovery and timeless philosophical wonder, where the fabric of reality woven from the strangeness of quantum mechanics reflects our own struggle to understand existence. The universe whispers through the mathematics of particles and the poetry of galaxies, and yet, in the quiet of our own thoughts, the mystery remains as intimate as a breath. Science has offered us revelations of startling clarity. We know that atoms born in the hearts of long-dead stars make up our bodies, that every thought is a cascade of quantum events in the theater of the brain, that space-time itself shimmers with uncertainty. These are triumphs of reason, achievements that pierce the darkness with light. Yet the brighter the light, the deeper the surrounding shadow. For with every discovery, the horizon of the unknown stretches farther, pulling our meaning-seeking minds into an even vaster mystery. This tension between the clarity of science and the persistence of mystery defines the modern human spirit. We no longer look to the heavens as children seeking a parental God to explain it all. Instead, we face an indifferent cosmos, elegant yet silent. Some feel the chill of that silence as existential dread. If everything is random and fleeting, if we are but quantum accidents, what anchors our purpose? What endures when stars themselves will one day burn out? But this same realization can be reversed like a Mobius strip, revealing an unexpected comfort. To be woven from the same fabric as the stars is to belong in a way no myth ever promised. The absence of a preordained meaning does not condemn us to despair. It liberates us to create meaning. The cosmos is not a stage on which we are merely spectators. We are the cosmos self-aware, wondering at its own grandeur. Our consciousness is not an afterthought, but a continuation of cosmic evolution, an emergence that allows the universe to know itself. Quantum theory deepens this connection in ways both unsettling and exhilarating. At the subatomic level, reality defies the neat categories of classical logic. Particles exist in superpositions, only crystallizing into definite states when observed. Entangled particles remain mysteriously linked across light years, as if distance were an illusion. These revelations are not merely scientific curiosities. They challenge our very intuitions about separateness and identity. If reality itself is relational and probabilistic, where do we draw the line between observer and observed, between mind and matter? For centuries, philosophers have wrestled with the same boundary. Is consciousness an accidental byproduct of neural complexity, or does it reveal something fundamental about the universe? Some interpretations of quantum mechanics flirt with the notion that observation awareness itself plays a role in shaping reality. Others caution against leaping to metaphysical conclusions. Yet even the most cautious admit that consciousness remains one of the deepest mysteries of all, as elusive as the quantum vacuum that hums with invisible energy. In this tension lies both the danger of unfounded mysticism and the invitation to profound wonder. To embrace the mystery is not to surrender reason. It is to recognize the limits of certainty and the vastness of possibility. Science gives us models, measurements, predictions. Philosophy gives us the tools to ask what those discoveries mean. Between them, we are not left with cold equations, but with an even richer story. One that includes awe, humility, and the courage to dwell in uncertainty. Existential anxiety is the shadow that follows this courage. When we confront our mortality in the light of a universe that will one day fade into heat death, the temptation to despair is real. Yet the very finitude of life sharpens its meaning. Each moment becomes more precious when we understand its rarity. The fleeting nature of our existence does not diminish its value. It magnifies it. To know that consciousness will flicker only for a cosmic instant is to feel, paradoxically, more alive. Connection emerges as a counterpoint to despair. Though we are mortal, we are not isolated. Every human thought, every act of kindness, every spark of curiosity is a thread in a cosmic tapestry. The atoms that compose our bodies were forged in the hearts of ancient stars. The photons that strike our retinas began their journey before life existed on Earth. We are bound to one another and to the universe itself, not by belief alone, but by the physics of our being. To see our consciousness as part of this cosmic story is to accept that meaning is not handed down from above, but woven from within. It is the story we tell through science and art, through love and inquiry, through the simple act of noticing that we are here at all. We are both question and answer, both fleeting and eternal, in the sense that our matter and energy will continue long after our individual lives end. In the quantum cosmos, certainty is elusive and permanence an illusion. Yet, within that uncertainty lies the freedom to shape a personal and collective sense of purpose. We need not resolve every paradox to find meaning. Perhaps the embrace of mystery is meaning itself. To live with curiosity, to marvel at existence without demanding that it be anything other than what it is, this may be our greatest act of participation in the grand, unfolding universe. Toward a new understanding, the mystery remains from the very beginning. Humanity has chased the dream of certainty. We built our first models of the world on the bedrock of reason, confident that with enough measurement, enough equations, the universe would eventually yield every secret. Classical physics once seemed to promise this, a clockwork cosmos where every motion could be predicted, every mystery solved with the sharp blade of logic. For centuries, that vision gave us comfort and a belief that reality, at its heart, was a perfectly legible book. waiting for us to turn its final page. And yet, with the rise of quantum theory, that confidence fractured. What once appeared solid dissolved into probability. Particles began to behave like waves, their positions and momenta dissolving into clouds of uncertainty. The very act of observing them seemed to alter what was observed. Reality, it turned out, was not a passive stage set for our instruments, but an unpredictable drama that defied our expectations. The more deeply we peered into the quantum realm, the more the ground beneath our feet shifted. Certainty gave way to an ever-widening horizon of questions. Here lies the great paradox of modern science. Every discovery expands our knowledge and simultaneously reveals the vastness of what we do not know. Quantum entanglement shows particles communicating across impossible distances, as though space itself were merely a suggestion. The vacuum of empty space seethes with hidden energy, a restless ocean beneath the calm surface of nothingness. Consciousness, that intimate theater of our own awareness, remains as mysterious as the birth of the universe itself. In these mysteries, science and philosophy meet not to settle debates, but to deepen them. For the seekers of truth, this is both exhilarating and unsettling. Our tools grow sharper, our mathematics more subtle, our experiments more precise. Yet with each layer peeled back, another appears, more elusive, more strange. The universe is not a puzzle to be solved once and for all. It is a living riddle that keeps remaking itself as we ask. Even time, that most familiar dimension of our existence, refuses to behave as we once believed. In the dance of relativity and quantum mechanics, past and future blur, and the present becomes a fleeting whisper. This is where science touches philosophy, and where philosophy brushes against the edge of the ineffable. We are forced to ask, is reality something we discover or something we create in the act of observing? Are the laws of physics eternal truths, or merely the patterns our minds have evolved to see? Perhaps the deepest structures of the cosmos are not separate from consciousness, but entwined with it. As inseparable as light and shadow, there are those who yearn for a final theory, a single elegant equation that explains everything from the birth of galaxies to the flicker of thought behind the human eye. And there are those who suspect that such an ultimate explanation will forever slip beyond our reach, like a horizon that recedes no matter how far we travel. The tension between these visions, between the dream of ultimate clarity and the humility of infinite mystery, is the heartbeat of our intellectual adventure. It is tempting to imagine that we stand on the brink of revelation, that the next breakthrough in physics or neuroscience will close the circle. But perhaps the very structure of reality resists closure. Perhaps the universe, in its deepest essence, is not meant to be fully known. If so, this is not a failure, but a gift, a cosmos alive with wonder, urging us to keep asking, to keep searching, to keep imagining. Consider how far we have come, from the certainty of Newton's mechanics to the ambiguities of quantum mechanics, from the comfort of classical determinism to the dizzying recognition of our own limits. Each leap has not only changed our science but transformed our understanding of ourselves. We are no longer passive spectators, but participants in a mystery that is at once mathematical and profoundly personal. The journey from the tangible to the transcendent does not end in despair, but in a quiet, luminous recognition. Reality is richer than our concepts, more intricate than our equations, more profound than even our wildest speculations. We may never hold the final key, but the very act of reaching, of daring to question, is its own form of revelation. The universe does not simply invite comprehension, it invites awe, and so the mystery remains not as an obstacle, but as a companion. The cosmos whispers through the language of physics and the silence of consciousness alike, reminding us that the quest itself is the meaning. We walk forward, not toward a final answer, but into an ever-deepening wonder, carrying with us the echo of questions that may never be silenced.